Hello students, so we are continue with chapter 3 intensity transformation and spatial filtering. In that intensity transformation functions, so piecewise linear transformation and about histogram processing. So now in piecewise linear transformations, contrast stretching is one of the simplest piecewise linear functions in a contrast stretching transformation. So low contrast images can result from poor illumination, lack of dynamic range in the imaging sensor, or even wrong setting of a lens aperture during image acquisition. So the idea behind contrast stretching is to increase the dynamic range of the gray levels in the image being processed. Intensity level slicing means highlighting a specific range of intensities in an image. So in other words, we segment certain gray level regions from the rest of the image. Now in the figure A, which shows a typical transformation used for contrast stretching, the locations of points R1, S1 and R2, S2 control the shape of the transformation function. If S1 equal to S1 equal to R1 and R2 equal to S2, the transformation is a linear function that produces no changes in gray levels. So if R1 equal to R2 and S1 equal to 0 and S2 equal to L minus 1, then the transformation becomes a thresholding function that creates a binary image. So we can see that in figure B. So here intermediate values, which are AR1 S1 B and AR2 S2 B, produce various degrees of spread in the gray levels of the output image. So the affecting it contrast. So in general, R1, R2 and S1, S2 is assumed so that the function is single valued and monotonically increasing. So this condition preserves the order of gray levels, which preventing the certain of intensity artifacts in the processed image. Figure B shows an 8-bit image with low contrast. Figure C shows the result of contrast stretching obtained by setting AR1 S1B equal to AR min 0B and AR2 S2B equal to AR max, which is L minus 1B. So where the R min and R max denote the minimum and maximum gray levels in the image respectively. So thus the transformation function stretched the levels linearly from their original range to the full range 0 to L minus 1. So in figure D shows the result of using the thresholding function defined previously with R1 equal to R2 equal to M, the mean gray level in the image. So the original image on which these results are based is a scanning electron microscope image of pollen magnified approximately 700 times. So now highlighting a specific range of gray levels in an image often is desired. So applications include enhancing features such as masses of water in satellite imagery and enhancing flows in X-ray images. So there are few ways of doing level slicing, but most of them are variations of two basic themes. One approach is to display a high value for all gray levels in the range of interest and a low value for all other gray levels. So this transformation is shown in figure A, which produces a binary image, and the second approach based on the transformation, which is shown in figure B. So brightness the desired range of gray levels but preserves the background and gray level tonalities in the image. So we can see here in the figure A is an erotic algorithm near the kidney. It is an erotic angiogram near the kidney area. So the objective of this example is to use intensity level slicing to highlight major blood vessels that appear brighter as a result of an injected contrast medium. So figure 2 here, figure B shows the result of using transformation in form of the figure A with the selected band near the top of the scale because the range of interest is brighter than the background. So the net result of this transformation is the blood vessel and parts of the kidneys appear white. So in the other hand, interest lies in the actual intensity values of the region of interest. We can use the transformation in figure B. So figure C shows the result of using such transformation in which the band of intensities in the mid-gray region around the mean intensity was set to black. So now a bit plan slicing. Instead of highlighting gray level ranges, highlighting the contribution made to total image appearance by specific bits might be desired. Suppose that each pixel in an image is represented by 8 bits. So imagine that the image is composed of 8 1-bit planes. So ranging from bit plane 1 for the least significant bit to the bit plane 8 for the most significant bit. So in terms of 8-bit bytes, plane 1 contains all the lowest order bits in the bytes comprising the pixels in the image, and plane 8 contains all the higher order bits. So this figure is illustrate these ideas. So now this figure shows an 8-bit grayscale image and figure B through 1. So here it's 8 1-bit planes with figure B corresponding to the lowest order bit. So observe that the 4 higher order bit planes especially last to contain significant amount of variety of the data. The lower order planes contribute to more subtle intensity details in this image. So the original image has a gray border whose intensity is 194. So to see why consider a pixel and say that the middle of the lower border of 3.14 A. Here the corresponding pixels in the bit plane starting with the brightest order plane have values 1 1 0 0 0 0 1 0, which is the binary representation of that code. The value of any pixel in the original image can be similarly reconstructed from the corresponding binary valued pixels in the bit planes. So in terms of the intensity, the transformation function, it is not difficult to show that the binary image of the 8-bit plane of an 8-bit image can be obtained by the processing the input image with the thresholding intensity transformation function that maps all the intensity between 0 and 127 to 0 and maps all the levels between 128 to 125. So now figure A shows an image constructed using bit planes 8 and 7. So the reconstruction is done. So this is nothing but the converting the nth significant binary bit to the decimal. So each plane used is multiplied by the corresponding contrast, and all planes used are added to obtain the grayscale image. So in figure A, we multiplied bit plane 8 by 128, bit plane 7 by 64 and added the 2 planes. In figure B, it shows the note that the background of this image has participle false continuing, so false counting. So this effect is reduced significantly by adding the 5th plane to the reconstruction. And in figure here see it illustrates using more planes in the reconstruction, we would not contribute significantly to the appearance of this image. So now histogram processing. In that we will see histogram equalization, histogram matching, local histogram processing, and about using histogram statistics for image enhancement. So now first is histogram processing. So histograms are the basis of numerous spatial domain processing techniques. So histogram manipulation can be used effectively for image enhancement. So in addition to providing useful image statistics, we will see in subsequent chapters that the information inherent in histogram also is quite useful in other image processing applications, such as image compression, segmentation. So histogram are simple to calculate in software and also lend themselves to economic hardware implementations, which making them a popular tool for a real-time image processing. So there are 4 types: histogram equalization, histogram matching, local histogram processing, using histogram statistics for image enhancement. So the histogram is of a digital image with gray levels in the range of 0 to L-1 is a discrete function h of Rk equal to Nk, where Rk is the kth gray level and Nk is the number of pixels in the image having gray level Rk. It is common practice to normalize a histogram by dividing each of its values by the total numbers of pixels in the image, which is denoted by N. So a normalized histogram is given by Prk equal to Nk upon N. For k equal to 0 or 1, Pl-1. So Prk gives an estimate. Prk gives an estimate of the probability of occurrence of gray level Rk. Now, as an introduction to the role of histogram processing in image enhancement, consider this figure, so which is a pollen image of the figure shown in 4 basic gray level. Characteristics are dark, light, low contrast and high contrast. So the right side of the figure shows the histogram corresponding to these images. So the horizontal axis of each histogram plot corresponds to gray level values, which are Rk. The vertical axis corresponds to the values Hrk. So Hrk equal to Nk or Prk equal to Nk by N. If the values are normalized, so thus it indicated previously, these histogram plots are simply plots of Hrk equal to Nk versus Rk or Prk equal to Nk upon N versus Rk. So in the dark image, that the components of the histogram are concentrated on the low side of the gray scale. So similarly, the components of the histogram of the bright image are biased towards the high side of the gray scale. So an image with low contrast has a histogram that will narrow and will be centered toward the middle of the gray scale. So we see that the components of the histogram in the high contrast image cover a broad range of the gray scale, and further that the distribution of pixels is not too far from uniform, which very few vertical lines being much higher than the others. functions, and let the variable r represents the gray level of the image to be enhanced. So in the initial part of in this, that assume that r has been normalized to the interval 0 to 1 with r equal to 0 representing black and r equal to 1 representing white. So we consider a discrete formulation and allow pixel values to be in the interval of 0 to L minus 1. So for this one for R satisfying these conditions, we focus attention on transformations, which is intensity mappings of the form. So S equal to TR, so where 0 less than equal to R less than equal to L minus 1. So that produce an output intensity level S for every pixel in the input image having intensity R. So we assume that TR is a monotonically increasing function in interval 0 less than equal to R less than equal to L minus 1 and 0 less than equal to TR less than equal to L minus 1 for 0 less than equal to R less than equal to L minus 1. So in some formulations to be discussed later, we use the inverse R equal to T raised to minus 1 into S, where 0 less than equal to S less than equal to L minus 1. So the requirement condition A, that TR be monotonically increasing, guarantees that output intensity values will never be less than corresponding input values. So the condition B guarantees that the ranges of output intensity is the same as the input. So here it satisfies condition A and B. So here we can see that if it is possible for multiple values to map a single value and still satisfy these two conditions, that is monomorphic transformation. So here figure A represents the problem if we wanted to recover the values of R uniquely from mapped values. So this would be possible for inverse mapping of SK in figure A, but the inverse mapping of SQ is range of values, which of course prevents us general from recovering the original value of R that results in SQ. So as figure B, it shows the requiring that TR be strictly monochromic, guarantees that the inverse mapping will be single value. Now, the intensity levels in an image may be viewed as a random variables in the interval 0 to L minus 1. So here the fundamental descriptor of a random variable is its probability density function. So that PR of R and PS of S denoted as the PDFs or S or R respectively. So where the subscripts on P are used to indicate that PR and PS are different functions in general. So here a fundamental result from basic probability theory is that if PR of R and TR of R are known and TR is a continuous and differentiable over the range of values of interest, then the PDF of transferred variable S can be obtained using simple formula. So PS of S equal to PR of R dr upon ds. So now a transformation function of particular importance of image processing has the form S equal to T of R equal to L minus 1, 0 to R PRW DW. So to find the PS of S corresponding to the transformation, so we use this equation. We know from the Lagrange's rule in the basic calculus that the derivative of a definite integral with respect to its upper limit is the integrated evaluated at the limit. So there is a ds upon dr equal to dt of r upon dr. So where L minus 1 d upon dr equal to limit has 0 to r PRW dW, which is equal to L minus 1 PR of R. So substituting this result for ds upon dr, so and keeping in mind that all the probability values are positive, so PR of S equal to PR of R equal to dr upon ds. So we can get here 1 upon L minus 1, which is 0 greater less than equal to S less than equal to L minus 1. So we recognize from the PS of S in the last line of this equation as a uniform probability density function. So we have demonstrated that performing the intensity transformation in this equation, which yields the random variables S characterized by a uniform PDF. So if we have cases like continuous values of histogram and discrete, then the equations are for continuous signal. This is the continuous case. S equal to T of R equal to L minus 1, limits of 0 to R to PRW dW. And for the discrete case is given by Sk equal to T of Rk equals to L minus 1, which is say equal to 0 to K, 0 from K, PR of Rj equal to L minus 1, which is J equal to 0 to K, Nj upon Mn equal to L minus 1 upon Mn, which has limit 0 to K Nj, where K is equal to 0 to L minus 1. Now this figure shows the 4 images. So here figure B shows the result of performing histogram equalization on each of these images. So the first three results shows a significant improvement. So histogram equalization did not produce a significant visual difference in the fourth image because the histogram of this image already spans the full spectrum of the grayscale. So the transformation functions used to generate the images in figure B are shown in this figure. So these functions are generated from the histogram of original images. So using that equation, so note that transformation has a basic linear shape, again indicating that the gray levels in the fourth input images are nearly uniformly distributed. So the histogram of the equalized images are shown in figure C. So it is of the interest to note that while all these histograms are different, the histogram equalized images themselves are visually very similar. Now the method used to generate a processed image that has a specified histogram is called histogram matching or histogram specification. So in continuous gray levels R and Z, and let PR of of R equal to Pz of Z denote their corresponding continuous probability density functions. So in this notation, and IZ denote the gray levels of the input and output images respectively. So we can estimate PR of R from the given input image, while Pz of Z is the specified probability density function that we wish the output image to have. So let's be a random variable with the property S of TR equal to limitations are 0 to R PR W dW, where W is a dummy variable of integration. We recognize this expression as a continuous version of histogram equalization, which is given in equation 4. So suppose next that we define a random variable Z with the property Zz equal to 0 to Z Pz of T dt equal to S, where the T is a dummy variable of integration. Now, as we know the values of S and G and AZ from the previous slide, so therefore that the Z must satisfy the condition. So the transformation TR can be obtained in that once PR of R has been estimated from the input image. Similarly, transformation function CZ can be obtained using equation 11, because Pz of Z is given. So mapping is from S to Z is equal to Z equal to G raised to minus 1 of S. So here is the histogram matching example, other example. So assuming the continuous intensity values, suppose that an image has the intensity PDF PR of R equal to 2R upon L minus 1 raised to 2 for 0 less than equal to R less than equal to L minus 1 and PR of R equal to 0. So for other values of R, find the transformation function that will produce an image whose intensity PDF is Pz of Z equal to 3Z square upon L minus 1 raised to 3. For 0 less than equal to Z less than equal to L minus 1 and Pz equal to 0 for the other values of Z. So first we have to find the histogram equalization transformation for the interval of 0 to L minus 1. So PR of R equal to 2R upon L minus 1 raised to 2 and 0. So here it is for 0 less than equal to R less than equal to L minus 1, otherwise it will be 0. So it will find the transformation function that will produce an image whose intensity PDF is Pz of Z equal to 3Z square upon L minus 1 upon 3 raised to 3. So for 0 equal to less than equal to Z less than equal to L minus 1, or if 0 then it is in the then if there is no this equation, then it is 0. Now here obtain PRRJ from the input image and then obtain the values of Sk, sound the value to the integer ranges which is from 0 to L minus 1. So here Sk equal to TRK equal to L minus 1. The histogram equalization transformation for the an input image S equal to T of R equal to L minus 1 0 to R, which is PR of W dW equal to L minus 1 from 0 to R 2W L minus 1 square dW R square L minus 1. For the same, find the histogram equalization transformation for the specified histogram. Here ZZ equal to this equation, and the transformation function Z equal to L minus 1 raised to square and S whole square 1 by 3 equal to L minus 1 square R square upon L minus 1 raised to 1 by 3 and L minus 1 R square raised to 1 by 3. So here, if we have to obtain PRRJ from that input images and then obtain the values of SK, which is round the values to the integer range 0 L minus 1. So in that case, SK equal to TRK into L minus 1, which is have J equal to 0 to K PR into RJ equal to L minus 1 upon Mn, J equal to 0 to K and J. So it is used with specified PDF and obtain the transformation function GZQ round the value to the integer range 0 to L minus 1. So which is GZQ equal to L minus 1 epsilon I equal to 0 to Q PZ of ZJ equal to SK. So mapping from SK to ZQ equal to G raised to minus 1 of SK. So suppose that the 3-bit image has the value of L equal to 8 of size 64 by 64 pixels, has the intensity distribution shown in the following table. So which is get the histogram transformation function and make the output image with the specified histogram listed in the table on the right side. Suppose that the 3-bit image L equal to 8 of size 64 into 64 pixels has the intensity distribution shown in the following table. Get the histogram transformation function and make the output image with the specified histogram listed in the table on the right. So first step of the procedure is to obtain the scaled histogram equalized value. In that, S0 equal to 1, S1 equal to 3, S2 equal to 5, S3 equal to 6, S4 equal to 7, S5 equal to 7, S6 equal to 7 and S1 equal to 7. So the next step is to compute all the values of the transformation function G. So here GZ0 equal to 7, epsilon Z equal to 0 to 0, PZ of ZJ equal to 0.00. So similarly GZ1 equal to we can say J equal to 0 to 1 equal to 7 PZ0 plus PZ1 equal to 0.0. So we can get these values. GZ1 0.0020, GZ31, GZ55, GZ77, GZ2 0, GZ4 2 and GZ6 6. Here you can see that. So the third step of the procedure, we find the smallest value of ZQ so that the value ZQ is the closest of SK. So we do this every value of SK to create a required mapping from S to Z. For example, S0 equal to 1, then we see that 1, which is a perfect match in this case. So we have to correspond to S0 equal to Z3. So that is every pixel whose value is 1 in the histogram equalized image would map to a pixel value 3 in the histogram specified image. So in the final step of the procedure, we use the mapping in the table. So to map every pixel in the histogram equalized image into corresponding pixel in the newly created histogram specified image. So the values of resulting this histogram are listed in the third column of the table. Now in this figure it shows the image of Mars moon, which is taken by NASA's Mars Global Surveys. So figure B shows the histogram of figure A. So the image is dominated by the large dark areas resulting in the histogram characterized by a large concentration of pixels in the dark end of the grayscale. So at the first glance, one might conclude the histogram equalization would be good approach to enhances this message so that the details in the dark areas become more visible. So this figure shows the histogram equalization transformation obtained from the histogram shown in figure B. So the most relevant characteristics of this transformation function is how fast it rises from gray level to 0 to a level near 190. So this is caused by a large concentration of pixels in the input histogram having levels very near to 0. When this transformation is applied to the levels of the input images to obtain a histogram equalized results, the net effect is to map a very narrow interval of dark pixels into the upper end of the grayscale of the output image. So as shown in figure B, this indeed the case that the histogram of the image shown in figure C not how all the gray levels are biased toward the upper of the half of the grayscale. Now in this figure C here shows a manually specified function that preserves the general shape of the original histogram. So the improvement of the histogram specified image over the result obtained by histogram equalization is evident by comparing these two images. So it is the interest to note that the rather modest change in the original histogram was all that was required to obtain significant improvement in enhancement. So here figure C shows the figure C shows in figure D. So the most distinctive feature of the histogram is how its low end has shifted right toward the lighter region of gray